For our next transformation, let's look at compressions and stretches. You'll notice in our first example here, exploration 3, how the number is directly outside the function itself. What I mean by that is if our parent function is y equals absolute value of x, then what we're seeing here is that we have y equals 2 times absolute value of x. Notice how that 2 is outside the parent function. Or right here you see y equals 1/2 absolute value of x. Let's take a look at how those graphs are related to each other. So here we have our parent function y equals absolute value of x. And what we're going to do is transform our graph by applying the a value. As the a value changes, let's go from an a value of 1 and let's go higher to an a value of 2. Notice what the graph is doing. Okay? And then as we bring it back down, let's now go to an a value of 1/2. Notice what the graph is doing. Okay? Now it's kind of hard to describe what's happening here because some of you may say that this looks like a horizontal stretch or compression. Some of you may say it's a vertical stretch or a compression. But I'm going to try to explain what exactly is happening here. It's a little bit difficult with online technology, but I'll give it my best shot. Okay, so as we go to an a value of 2, notice what the graph does. I'm going to mark this place here and label this as y equals 2 absolute value of x. Then as I bring this graph back down, we're going to go to an a value of 1/2. Okay, so then here's our graph of y equals 1/2 absolute value of x. Here's where I'll try to explain what exactly is happening to the graph. If you can kind of imagine, I'm going to kind of create an analogy for you here. If you can imagine, imagine that you are, you have a ball of Play-Doh. Okay, so here's you, and you have a ball of Play-Doh, and what you want to do is you want to take your hands, and here's your hands, okay, and you're going to stretch this ball of Play-Doh, okay, and so if you imagine you stretch the Play-Doh, if you've ever done this before, you'll know that it kind of stretches up and down like this, right? So this is what's happening to the graph. As the graph is stretching from the parent function of y equals absolute value of x, let's say you take this point at 1, 1, and you stretch it, you're stretching it vertically. It's going up. The y value of 1 now goes to a y value of 2. For another point, if let's say you take this y value of 2 and you stretch it, this y value of 2 now gets over to a y value of 4. You stretch it, you double it basically. If we do another one, let's say on our parent function we have a y value of 5. It gets stretched to a y value of 10. So in essence, what you're doing is you're doubling all of the y values. All the y values get stretched vertically, and if you notice, the x values actually stay the same. Now likewise, if we were to go the other way, so let's say now, here's you, and now let's say you're gonna squish this, right? So what you're gonna do is you're gonna take your hands and you're going to now squish this ball of Play-Doh. And so in essence what you're doing is you're pushing everything in together like this, right? And so you can see here that now the original y value of 1 gets squished to a y value of 1/2. This y value of 2 gets squished to a y value of 1. If you had a y value of 5, it gets squished to a y value of 2.5. Okay, so you can basically see here that this is creating a vertical stretch or vertical compression. Okay, so going back to our graph here, I want to show that to you again. Notice as we start from the parent function, as that a value gets larger, now imagine that this is Play-Doh and you're stretching this ball of Play-Doh up. So now you have y equals 2 absolute value of x. You're stretching it vertically like that. Or if you go to an a value of 1/2, you're now squishing this absolute value, this v-shaped graph, you're squishing it down. Imagine you have that hand and you're squishing it down on the table. You're pushing it down, and so you can see that graph gets squished. This is getting compressed vertically. That's the more appropriate term. This graph is getting compressed vertically as a value goes to 1/2. Okay? Or if a is basically less than 1, but also greater than 0. Okay? Let's take a look at our worksheet again. So what we're saying here is that if the a value is greater than 1, then what you're doing to the original graph is you are stretching it vertically by a factor of a units. If a value is between 0 and 1, then the graph is compressed vertically by a factor of a units. One thing to keep in mind is that x always stays the same. And the y value is what gets multiplied by a factor of, in this case, let's just call it a, by a factor of a. Okay? Let's go on to our next type of compression and stretch. Okay? So now you'll notice that we have the parent function y equals x squared. And what we're going to do now is we're going to say y equals f of 4x is the same thing as saying 4x squared, like that, all within the parentheses. You're replacing the x with the 4x. Okay, so the 4x goes where the x would have gone. Okay, or we'll also have the graph of y equals half x squared, like that. Quantity half x squared. Okay, so let's take a look at what's going to happen here on the graph. Let's go back to our graph, Desmos. And now let's look at our new graph of y equals x squared. Okay, so here we have it, y equals x squared. And what we're going to do is now, if you notice here in slide 10, we have y equals bx squared. And so we're going to adjust that b value. And let's see what's happening to the graph. Kind of imagine what's happening as that b value gets larger. Or if I go back to the parent function, if that b value gets smaller, what's happening to the graph? Hopefully what you're seeing is that now we're compressing this parabola. Think of how your hands are now left and right, and now you're kind of like squishing it together. Squish, 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 right? You're compressing that parabola horizontally now, versus the other way, if you stretch that parabola horizontally, that's what's happening to the graph like that. Okay, so let's put all this together. What we have is when that b value gets larger and larger, we're going to 4x, right? Y equals 4x squared. There it is. Okay, so this is the graph of y equals 4x squared. And then now let's bring it the other way as well. And we're going to stretch this parabola all the way to y equals half x squared. Okay. Again, I like to paint you a visual. I like to give you an analogy of what's going on here. Okay, so imagine now, here you are, and you are going to take those hands, right? Here's your hands. There you are. Bad drawing, I know. And then what you're going to do is you're going to take your Play-Doh, and now you are stretching this horizontally like this. That's y equals half x squared. We are stretching the graph horizontally, as you can see here. Okay, so we take our parent function. If we used to have an x value of 1, well, now it's at an x value of 2. See, it got stretched horizontally. If you used to have an x value of 2, then now you're stretching that to the x value of 4. Okay, versus the other way, if you were to imagine now you're angry, you want to compress this, you're going to take your hands, you're going to compress that Play-Doh, and so it now gets really squished in here, right? You're squishing it together, you're pushing it together. And so as you're pushing it together, if you had an x value of 1, now based on our equation of y equals 4x squared right there, what we're saying is that the x value of 1 now needs to get compressed to an x value of 1/4. Okay, if you had an x value of, let's see, what do we have here? An x value of, right here, 3, right? You're gonna compress that all the way to an x value of 3/4. Okay, so in essence, what you're seeing here is that if you have your, let's say your function, your original function was f of x equals x squared, but then you changed it so that there was a 4x in there. So if you have a 4x squared in there, you kind of want to say, how do I make this go back to my original statement, right? How do I get that value to be the same as the x? And so what you're seeing here is that you need to multiply that 4 times the 1/4 to be able to get to that original statement. So that's why you have to multiply it by a factor of 1/4. So everything gets multiplied by 1/4. If you multiply 1 by 1/4, you get 1/4. If you multiply the 3 by 1/4, you're going to get 3/4. That's what's happening there. Okay. So let's go back to our worksheet. Okay, and so what we're saying now is that if the a value is greater than 1, the graph is going to get compressed horizontally by a factor of 1 over a units. Okay, so it's kind of like thinking in the inverse relationship here. If that a value is greater than 1, the graph is getting compressed. It's getting kind of squished in. If the a value is between 0 and 1, then the graph of the original function will get stretched horizontally by a factor of 1 over a units. Now, unlike our previous stretch and compression, the vertical one, where x stayed the same and y gets multiplied by a factor of a, now with a horizontal stretch, what we're saying is that the y value stays the same. What you're doing is you are directly affecting the x value right there. You can see it's directly affecting the x value. So then this time now, x gets multiplied by a factor of 1 over a.